The SAFI GSE is a leading structural engineering software for the analysis and design of structures for concrete, steel, wood, and aluminum. The software is a great tool to help design and analyze various structures with many automated design functions that still allows any user to personalize any design elements. The SAFI GSE supports the latest design standards for Canadian, American, and international standards for concrete, steel, wood, and aluminum. In this video, we will create, analyze, and design a simple two-story aluminum braced frame shown on the screen. The building has 3 bays in each direction with a mezzanine. It is submitted to a live load on the mezzanine, snow load on the roof, and wind load on the left side wall. The design will be carried out per the 2015 Aluminum Design Manual. Let's start by creating a new model. We need to define the model as a 3D model and set the units to imperial units. We can now define the elevation of the stories and create a grid to match the dimensions of the bays. We will assume the stories of 12 feet high. The grid must be placed in the horizontal plane, which is XZ in the GSE. We can then create evenly spaced grid lines along X and Z. The bays have 20 feet along the x-axis and 23 feet along Z. The first step is to create the joints at the base of the columns. The fastest way to create the joints is to drag a window around the grid to create all joints in a single operation. The columns are created by extruding the joints in the Y direction. Once this is done, we can isolate each story to create the beams. Using the same method we used for joints, we can create the beams by making a window around the grid. We can then go ahead and delete the members that we do not need. We then repeat the same operation for the roof level. The order in which operations are done is not important. We will simply create all the sections at this point. The same 6061-T6 grade will be used for all sections. We will use parametric wide flange sections for beams, a hollow square tube for columns, and an angle section for bracings. We have gone ahead and created a few sections to show the procedure, but we will end up with 6 sections for this model. Now we will assign the sections to the beams. Once all the sections are properly defined, we can assign them to the members. For the purpose of this example, we will assume the beams are connected to the columns by shear plates. It is a good time to assign the end releases at both ends of all the beams. Now that we have assigned the sections to the beams, we will go ahead and create the floors. In this example, the floors are made of an aluminum deck supported by joists. In the GSE, floors are modeled by load surfaces. The load surfaces are used to transfer loads to surrounding members. In the case of the joists, the floor loads are transferred to members as concentrated loads. They are also used to model the diaphragm effect on the deck. The deck stiffness is defined using the finite element plates acting in membrane only. Load surfaces can be generated automatically based on a selection or one at a time. Now that we've created the floors, we will go ahead and create the walls. Walls can be created in the same way. Here, we create the wall surfaces one at a time, but they could be created as it was done for the floors. In this example, the wall surfaces will transfer wind loads as uniformly distributed loads to columns. Here, we don't define any diaphragm as the stiffness of the cladding cannot be used as lateral force resisting systems. We are now ready to define the basic loads in SAFI. Now that the geometry is completed, we can add the loads to this model. The first step is to define the basic loads used. For this example, we need to define the dead loads, live loads, snow loads, as well as the wind loads. In addition to the basic load names, their types must be selected in order to use the load combination wizard. Now that we have defined the basic loads, we are ready to apply the loads to the model. Once the basic loads are defined, we can define the gravity load, which represents the self-weight of the elements. It is defined as the dead load and acts as the negative y direction. It is defined as a dead load and acts in the negative y direction. We then define the other gravity loads on the floor surfaces as uniform pressure loads. We define a dead load and a live load on the mezzanine. We then add a dead load and a snow load on the roof. And finally, we add the wind load on all the wall surfaces. In this example, we forgot to assign the sections to columns earlier in the model as well as the support conditions. We can simply go back and make those modifications to the model. We will use the special selection tool to select the columns and assign the section. In the same way, we can also select the base joints and assign the support conditions. Now we can go ahead and create the bracings. There is no automated way of creating the bracings in the program, so we will need to create them manually, member by member. We will assign the angle section defined earlier to the bracing members and also define the end releases. We will also define the bracings as tension-only members. We can go ahead and attach the bracing members at the top of their crossing points. We can then copy these bracings to the opposite wall. And finally, we can then repeat the same series of operations to create bracings in the other direction. Now that we have created the bracings, we can go ahead and define the load combinations. We will generate the load combinations using the load combination wizard. The load combinations are defined using the ASCE 7 code without using load patterns. At this point, we are now ready to recalculate and review the design parameters. Most design parameters, such as unbraced length and bending, buckling lengths in compression, and span lengths for deflections, can be calculated by the system based on the geometry. We can then review the calculated values for any member in the Aluminum tab of the Member Attributes window. Any calculated value can be modified. We can then see that the system accounted for spacing of the joists in determining the unbraced lengths and bending. We can also see that the system accounted for the joints created at the crossing of the bracing members and their buckling lengths. We are now ready to define the welds. The influence of the welds is defined by specifying the ratio of welded area on each flat segment of the sections. In this example, we assume that only the columns have welds. We will define the ratio of the welded area, assuming that the shear plates are 1/2 thick, which gives a ratio of 45.5%. The ratio will be applied to all sides of the columns for simplicity. We are now ready to analyze and view the results. Now that the model is complete, we can run the analysis and design. The design is done per the 2015 Aluminum Design Manual, which requires to perform a second-order analysis of the model. It also requires that the stability should be verified according to the direct analysis method instead of the conventional buckling length method. Once the analysis is completed, the resulting unity checks can be viewed on the main screen. As a last step, we can look at some additional results. Several other results are available. It is possible to view the elastic stress distribution on any member of the model. It is also possible to view the forces distribution on any member of an envelope or a specific load combination. All intermediate design results are also available in order to validate the calculations made by the program. Thank you for watching. Don't forget to subscribe to SAFI's YouTube channel and visit our website www.safi.com to stay updated on the latest features of the software.